Shortly before Halloween in 2020, NASA compiled a list of the most terrifying worlds. Among others, they included 6 exoplanets. Each of these objects' environments is not just extremely harsh for any living organism, even finding oneself in their comparatively close proximity may prove to be fatal. The first object on the list is a black gas giant, designation TRES-2b. This celestial object orbits the star TRES-2, which is a yellow dwarf lying as far as 718 light-years away from us. Let's take a closer look at it. Due to some unique properties of the chemical composition of the surface of TRES-2b, the planet absorbs over 99% of all the light shed on it. The nature of these properties remains a mystery, and chances are there are some chemical reactions taking place on the surface that we have never registered on any similar object before. And it is these properties that make TRES-2b the darkest exoplanet on the astronomical map of today. This gas giant was discovered on the 21st of August 2006, with more details on its characteristics obtained several years later. The mass of TRES-2b is 1.2 Jupiter masses, and its radius measures 1.27 times that of Jupiter. The atmosphere is as scorching as 1000 degrees Celsius, which gives the exoplanet a faint red glow like that of embers. Still, in spite of its gloomy looks, TRES-2b doesn't really qualify to be called the most dangerous place in the universe. There are many more objects lurking in space that are more terrifying than that. Let's see some more inhospitable ones. Here is another exoplanet, designation 55 Cancri E. It lies in the system of a Sun-like star, designation 55 Cancri A. This celestial object was discovered on the 30th of August 2004 by the Doppler spectroscopy method. Let's look at it in more detail. The planet's mass equals approximately 8 Earth masses, and its radius measures 1.875 that of the Earth. 55 Cancri E is tidally locked, and so it is always daytime on one side and nighttime on the other. That is why the side facing the host star is always heated up to a temperature reaching 2400 degrees Celsius, with the temperature on the night side 1300 degrees Celsius. These values are so high because the distance between the planet and its parent star is just 0.0183 astronomical units. Besides, volcanism on 55 Cancri E, which is thought likely to be there, causes dust clouds emissions. These clouds trap heat and effectively prevent it from escaping into space. The planet's orbital period is slightly under 18 hours. As for the atmospherical makeup, there is helium and hydrogen registered in it. There are also large amounts of carbon. Incidentally, this element is likely to form thick layers of graphite and diamonds in the planet's interior. 55 Cancri E isn't the only object in the planetary system of its host star. There are 4 other celestial objects orbiting it. The environments on these are by far more hospitable, which is the feature by which the 55 Cancri A system differs from the following object. It is dubbed Poltergeist, or PSR 1257+12c. This is an exoplanet lying in a pulsar system. The celestial object is located just 0.36 astronomical units from the system's center. This shows that Poltergeist wouldn't have survived a supernova that must have taken place before the pulsar had been formed. Consequently, the exoplanet is likely to have formed after this tremendous event, with the material for it coming from the nebula left after the explosion. According to another hypothesis, the pulsar may have formed after the merging of 2 white dwarfs. Unlike with a supernova, this process isn't always accompanied by a powerful blast. Still, as this is the first object of its kind we have discovered, science cannot give a definite answer as to its origins. The system with the celestial object lies 2,300 light-years from the Earth. Its mass is approximately 4 times that of our planet. As for its orbital period, it is around 66 days. Incidentally, the outstandingly powerful radiation emitted by the pulsar is enough to crumple any spaceship wanting to approach the mysterious exoplanet in its system. Even with all these properties taken into account, Poltergeist does not really qualify as the most dangerous exoplanet known to us. On approaching it, an astronomical body may simply get destroyed, but it would get positively vaporized in close proximity to the following object. The reason for this effect is the extremely high temperature on Kepler 70b, which is the hottest exoplanet known to us. The object orbits the subdwarf star Kepler 70. With a surface temperature higher than that on our Sun, it reaches 6,800 degrees Celsius. The object's mass equals 0.44 Earth masses, and its radius measures 0.76 that of the Earth. The celestial object's orbital period is 345 minutes. In other words, a day here is less than 6 hours long. Interestingly, the exoplanet regularly passes another object in the system, Kepler 70c, at a distance of 240,000 kilometers. To date, this is the closest that planets in space have been registered to pass each other. The extremely high temperature on Kepler 70b could be accounted for by the fact that this object may once have been part of its parent star. As for giving it the status of an exoplanet, it will take more evidence to confirm that it deserves to be given it, so this remains an open question. It should be mentioned that Kepler 70b is not the only celestial object we know of that interacts with its parent star so closely. Another object in similar conditions is the exoplanet known as WASP-12b. This celestial body lies 870 light-years away from our system. Its radius measures 1.93 times that of Jupiter, and its mass equals 1.46 Jupiter masses. WASP-12b is just 0.03 astronomical units away from its parent star. Due to this close proximity, the exoplanet has a temperature reaching as much as 2,200 degrees Celsius. The host star's extremely powerful gravitation slowly absorbs WASP-12b. Eventually, in approximately 10 million years' time, the exoplanet is expected to be destroyed completely. Bearing all this in mind, we will probably never delve any deeper into the nature of this exoplanet. It would appear that studying worlds of this kind cannot be high on scientists' list of priorities. However, some of these objects may happen to have some really unique features. Seemingly quite plain and ordinary, worlds like that may conceal many more dangers than would appear at first glance. When flying past the celestial body HD 189733b, for example, one might complacently think it a safe planet, as it resembles our Earth by its looks. But if one were to get as low as the level of its atmosphere, one would be exposed to some life-threatening dangers. For a start, the object's winds carry particles of silicate and develop velocities of 8,700 kilometers per hour. Besides, the rains on this planet cause precipitations of molten glass. The reasons for such hazardous weather conditions are extremely high temperatures and the atmosphere's peculiar chemical composition. Speaking about the exoplanet's orbital period, it is approximately 2.5 days. And it is highly likely that the object is tidally locked to its parent star. As usual, a quick overview of its main characteristics. HD 189733b is a bright blue gas giant orbiting an orange dwarf in the constellation Vulpecula. It lies just 63 light-years away from our system. The object's diameter is 1.1 times that of Jupiter, and as for its mass, it is 113% that of Jupiter. Interestingly, the distance between HD 189733b and its star is 30 times less than the distance between the Earth and the Sun and equals approximately 5 million kilometers. Due to its close proximity to the parent star, it has a constant surface temperature of as high as around 930 degrees Celsius on the day side, with the temperature on the night side never dropping below 425 degrees Celsius. Immediately on being discovered, the celestial body became a subject of investigations. In 2007, thanks to data obtained by the Hubble telescope, scientists found out that HD 189733b has a foggy atmosphere. Interestingly, when the planet transits between the observer on the Earth and its star, its atmosphere assumes a reddish hue. This effect could possibly be caused by the haze in the atmosphere. According to preliminary estimates, it consists of particles of iron, silicates, and aluminium oxide. Apart from that, the information beamed back by the Hubble telescope helped scientists establish that the planet's atmosphere contains water vapor, neutral oxygen, and an organic methane compound. Additional investigations revealed the presence of carbon monoxide on the day side of the planet. What prompted most questions, however, was the results of investigations revealing traces of methane of an unusual variety in the planet's atmosphere. This chemical element was shown to be in a peculiar fluorescent state when it emits electromagnetic radiation in the infrared range. This state of the substance is indicative of some unknown activity in the atmosphere of the exoplanet, which still remains to be found out. This is quite a clear-cut example of a situation when investigating an object like an exoplanet with an exceptionally harsh environment may yield unexpected results about some processes taking place there that will be a valuable contribution to science. And as the process of studying these worlds continues, they will remain no other than horror planets to us, as well as a solid reminder that we're more than just lucky to be the dwellers of our Earth. Earlier, in one of our previous videos, we have already taken a look at some terrifying and lethally dangerous worlds discovered in the vast expanses of space. With some of them extremely hot, others are located close to insanely powerful sources of radiation, and yet other ones are peculiar for some bizarre features on their surfaces. However, we haven't quite exhausted our list of the most horrifying planets, and now it's time to see some more. Our first stop is 202 light-years away from the Earth, destination K2-141, an orange dwarf. Its mass is roughly 0.7 that of the Sun, and its radius measures 68% that of our host star. With these parameters almost perfectly proportional, the star's temperature reaches 4,600 Kelvin, which is about 20% less than that of the Sun. And now to the planet in question. Just 0.007 astronomical units away from its star, there lies a really bizarre world, designation K2-141b. This rocky exoplanet is 5 times as massive as the Earth, with its radius 1.5 times as big as that of our Earth. All this gives us grounds to assume that the gravity on the planet's surface is at least twice as strong as that on our planet. The heavy metallic core, meanwhile, accounts for 20 to 50% of the planet's overall mass. It takes the celestial body about 6.5 hours to complete a full orbit around its parent star. Being extremely close, it is tidally locked to it. That is, it faces the star with one and the same side at all times. Observations show that the temperature on the planet's day side reaches 3,270 Kelvin or 3,000 degrees Celsius. This is enough not only to melt most rocks and metals, but also to effectively evaporate them. The day side of the planet is assumed to be covered with a lava ocean that never ceases to boil. The atmosphere is thought to be rather exotic, made up of steams of heavy metals and silicates. By contrast, the planet's night side is incredibly freezing. According to estimates, the temperature of most of its area is tens of times lower than that on the day side, and on balance, its values are supposed to be sub-zero. Mathematical modeling shows that this sharp temperature contrast gives rise to exceptionally strong winds whose speed reaches 1.75 kilometers per second. This is roughly 5 times the speed of sound, which means that the surface of K2-141b is continuously shaken by exceptionally powerful, deafening rumbling. It is assumed that on reaching the night side, atmospheric streams condense and precipitate on its surface in the form of fiery rain. This forms lava rivers, and eventually this molten metal makes its way back into a magma ocean to evaporate again later on and to continue this incredible fiery circulation. However, this infernal cycle affects only a relatively small part of the planet's night side. The thing is that masses of evaporated elements from the day side simply don't make it to the main part of the night side and precipitate somewhere on the border. That is why the central part of the night side is likely to be a freezing desert bound with layers of solid rocks. Remarkably, K2-141b is far from being the hottest planet that we know of. For example, there is an object referred to as Kelt 9b lying 670 light-years away from the Earth. Its surface is as hot as 4,600 Kelvin, which is approximately 4,330 degrees Celsius. Just to compare, the outer layers of almost all red dwarfs, for example, are much cooler, which means that in terms of temperature, this exoplanet is quite a match to stars. Its parent star, designation Kelt 9, is of a whitish-blue color and has a mass 2.6 times that of the Sun. As for its diameter, it is 2.3 times that of our star. The surface temperature of Kelt 9 is rather high at approximately 10,170 Kelvin, or a staggering 9,900 degrees Celsius. This largely accounts for the extreme conditions on Kelt 9b, which lies quite close by. Just 0.035 astronomical units away from its parent star, the planet completes a full orbit around its system's center roughly every 1.5 days. Kelt 9b is a hot gas giant. Compared to Jupiter, its mass is 2.8 times as big, and its radius measures roughly twice as much as that of the largest planet in our system. Based on today's notions about the composition of this type of planets, the inner part of Kelt 9b's atmosphere is supposed to be even hotter. Estimates allow for this value to reach as much as 11,000 Kelvin on account of heavy metal ionization. With this figure so exceptionally big, it appears that the planet's atmosphere should contain vaporized iron and titanium, alongside the elements we're used to in an atmosphere's composition, such as hydrogen or helium. Its close proximity to the parent star and the extremely high temperature cause the planet to gradually lose its atmosphere. By and by, powerful stellar wind blows it off into space, which is why the object is shrouded in a cloud of rarefied gas. This material will eventually be attracted and absorbed by the star. Interestingly, according to some estimates, the exoplanet loses up to 68 Earth masses every billion years. Theoretically, in a long while, Kelt 9b may well get stripped of all of its atmosphere and transform itself into a Chthonian planet. However, its parent star is likely to hit the final stage of its life cycle long before that, swallowing up and destroying all the celestial objects within its reach. The space objects we have just looked at are a living proof, as it were, of the fact that stars can destroy the planets close to them and not just warm them up. But incidentally, there are celestial objects out there in the universe that have experienced their parent star's wrath in full measure. One of such objects lies 4,570 light-years away from the Earth in the environs of a small star, designation V391 Pegasi. Now, the star is a white dwarf whose mass is twice as little as that of the Sun and whose radius is approximately 23% that of our parent star. The temperature of this celestial object is unbelievably high, at almost 30,000 Kelvin. All thermonuclear reactions in its interior would have run their course a long while ago. Up ahead are hundreds of billions of years of slow cooling, with the white dwarf eventually transforming into a black one. The planet we will look at, referred to as V391 Pegasi b, is in this ordinary star's environs. its lot is exceptionally amazing. According to mathematical modeling, the planet not only survived its progenitor star shedding its outer layers, but actually found itself almost within the star for some time. It is assumed that when the system's star V391 Pegasi transformed into a red giant, its outer layers, extremely rarefied by then, were almost brushing the planet's orbit. Their density became dozens of times lower than the atmospheric air we're used to, which means that the celestial objects devoured by the dying star remained whole for a while and didn't get destroyed at once. It goes without saying that they would have been losing their speed and dropped into the star's hotter and denser layers. Still, V391 Pegasi shed its outer layers sooner than V391 Pegasi b melted and ceased to exist as a whole object. At the moment, the exoplanet appears to be a gas giant, 3 times as massive as Jupiter. Its orbit passes 1.7 astronomical units away from its parent star, and it takes the planet approximately 1,170 Earth days to complete a full orbit around its system's center. It is still not entirely clear how this astronomical body managed to preserve such a big mass after its collision with the scorching hot layers of the star. Their influence was supposed to have destroyed the object's atmosphere completely. However, there is no doubt that the host star's collapse brought about some dramatic changes, both in terms of the exoplanet's orbit and its parameters. That is why it is hardly possible for us to ever find out what V391 Pegasi b was like before immersing in a sea of raging plasma. Space expanses conceal uncountable astronomical objects with the most bizarre properties. Some of them are almost totally invisible through regular telescopes, but can be detected by looking at radio wavelengths when exploring space. An example of such like celestial objects is pulsars, neutron stars spinning on their axes at a mind-boggling speed. These object spectra are peculiar for exceptionally fast and regular pulsations. That is why it is quite easy to detect another celestial body transiting between a radiation source like that and an observer on the Earth. This is precisely the way our next object of interest was discovered. But first we'll be looking at a pulsar which lies around 4,000 light-years away from the Earth. This neutron star boasts quite a long name. Here it is on the screen. And now let's check out its remarkable features. The pulsar's diameter is just a measly 20 kilometers, and its mass is approximately 1.4 that of the Sun. The object spins at an incredible rate, with roughly 10,000 rotations a minute, while continuously emitting powerful electromagnetic radiation impulses. Now the surface of the exoplanet, our next object of interest, is continuously exposed to these waves of lethal radiation, which makes it a hostile and forbidding place. It takes this planet just 2 hours to complete a full orbit around its system's center, and the distance to the pulsar is smaller than the Sun's radius, just 600,000 kilometers or 0.004 astronomical units. Incidentally, the celestial body's surface is bound by eternal cold and space as its parent star just barely emits thermal energy. The object's mass is around 330 that of the Earth, while its radius is 4 times that of our planet. This makes gravity on its surface as much as 20 times stronger than on the Earth. Estimates show the planet's average density to be about 23 grams per cubic centimeter, which is more than most chemical compounds we know. The planet is thought to be made up for the most part of crystallized carbon under a lot of pressure. Besides, the object's upper layers contain some oxygen, which is probably chemically bound with carbon. It is highly doubtful that a celestial body located so close to a star could possibly have survived a supernova event. It is more realistic to assume that the exoplanet formed after the progenitor star had come to the end of its life cycle and had transformed itself into a pulsar. The exoplanet could be a piece of debris left over from a white dwarf whose material would have dispersed for the most part. This makes classifying the exoplanet an especially difficult task. Still, whatever it is, this world remains one of the most dangerous and hostile ones lurking in the depths of the cosmos. 650 light-years away from the Earth, there lies IRC plus 10-16, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2,300 Kelvin or about 2,000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass is insufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, an amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half-arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is a comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant's structure accepted at the time, according to which all oxygen in stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around 1/1000th of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against a background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shockwave and the mind-boggling temperature in the epicenter will generate new elements that are not to be found in a star's interior. For example, uranium, gold and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. temperatures of any star's interiors are incredibly high. It is hardly surprising, as thermonuclear synthesis, that is the main energy source of all stars, can take place only in these extreme conditions. When two atoms of hydrogen merge, they produce an atom of helium and release an electron and several neutrinos. In addition, a great amount of energy is released during the process. Still, the hydrogen-helium synthesis isn't the only process that heats up stars. At higher temperatures, other elements may take part in chemical reactions as well, for example lithium, carbon or oxygen. In this case, cores of heavier elements are produced, such as sulfur, magnesium or phosphorus. Their charge is higher and they repel each other more robustly. Much more energy is needed to overcome this resistance. When a main sequence star depletes most of its hydrogen supply, it starts to expand and cool off. With time, it ends up as a red giant. It will continue to burn due to thermonuclear reactions of helium transforming into carbon and oxygen. The lighter the star, however, the less time it will continue to burn. Eventually becoming unstable, it sheds its outer layers and goes supernova. This leaves it a white dwarf with no resources to fuel any thermonuclear reactions anymore. With all its energy sources depleted, it is forced to gradually cool off. Interestingly, when the mass of a star is higher than a certain value, heavy thermonuclear synthesis may become the star's main energy source even after all hydrogen has been used up. Such celestial objects are referred to as Wolf-Rayet stars. This class of space objects was discovered back in 1867 by the French astronomers Charles Wolf and Georges Rayet. The scientists' attention was caught by anomalously bright emission lines of heavy elements in these stars' spectra. As for the inner makeup of these unusual celestial objects, it was accounted for much later. Stars of this class are generally heavy. They have quite a meager supply of hydrogen and are in the final stages of their revolution. Wolf-Rayet stars are extremely rare. To date, just a few hundred of them have been discovered in our galaxy. As for their overall count in the Milky Way, it is estimated that there can't be over 2,000 celestial objects of this class. Wolf-Rayet stars are subdivided into three main sequences depending on the prevalent element in the spectrum: nitrogen, carbon and oxygen sequences. Each of them, in its turn, is subdivided into several types. As for the hottest star in the studied universe, it falls into the category of the oxygen spectral sequence ones. The celestial body, which is now known as WR102, was discovered back in 1971. At first, it was mistaken for the optical counterpart of the X-ray source GX3+1. However, further observations revealed that there were two completely different objects. According to data acquired thanks to spectral analysis, the discovered star had unusually bright oxygen lines in its radiation spectrum. Thus, in 1982, WR102 and four more bright stars became the first to form a new class. Spectral analysis showed that the star's surface temperature reaches over 210,000 Kelvin. This makes WR102 approximately 36 times as hot as our Sun. The luminosity of this scorching hot object is unbelievable. It is estimated at over 380,000 times that of the Sun. WR102 lies about 10,000 light-years away. The star is located in the part of the sky with the constellation Sagittarius. Incidentally, in spite of its exceptionally high luminosity, it can't be seen with the naked eye, as it is too far away from us. WR102 currently belongs to the extremely rare star class WO2. Containing great amounts of oxygen and almost no hydrogen, it mainly relies on the merging of heavy cores of such elements as neon, carbon and oxygen as its sources of energy. To date, only 9 objects of this class have been discovered, with 4 of them located in the Milky Way and the other 5 in other galaxies. There are 2 factors that make oxygen spectral sequence stars rare. Firstly, there are very few of Wolf-Rayet stars around because only stars with a mass not less than 40 solar masses are potential candidates to become ones. Secondly, this class represents the final stage of evolution of stars of this type. The stage may last anything from 1,000 to 10,000 years, which is mere seconds in astronomical terms. Being of comparatively modest dimensions, WR102 is notably quite a dense star. With its radius measuring just 58% that of the Sun, its mass, on the other hand, is estimated at 15 to 18 solar masses. On its birth, it is thought to have been as heavy as 40 to 60 solar masses. Still, the high temperature and robust chemical reactions in the star's interior cause an exceptionally powerful stellar wind, whose particles' velocity is over 5,000 kilometers per second. It takes WR102 just a few months to lose 1 Earth mass worth of material on account of its stellar wind. At this rate of particle emission, the star is going to lose 1 Sun mass worth of material in the course of 10,000 years. There are no planets orbiting WR102, but it is shrouded in a gas envelope. Not dense and exposed to powerful ultraviolet radiation and strong stellar wind, the envelope gets contracted and ionized, which sustains its elaborate structure of protuberances and arches all around the star. According to a proposed theory, the gas cloud around WR102 may probably be remnants of the former hydrogen outer layer of the star. Another theory maintains that the cloud came to be as a result of the particle flow emitted by the star. WR102 is not the only outstandingly blistering place in the universe. For example, WR142, WR30A and WR93b, as well as the central star in the Bug Nebula NGC 6302, are as hot as around 200,000 Kelvin. Some white dwarfs may have almost the same surface temperature. However, all these are no match to neutron stars. When neutron stars are born, their temperatures may reach a staggering 100 billion Kelvin. Active neutrino emissions cool them off comparatively rapidly. But either way, the surface temperature of any neutron star is never less than a few 100,000 Kelvin. As for their cores, they must, admittedly, be hotter still. Having said that, it is highly improbable that the ultimate temperature record is ever going to be beaten. According to today's cosmological concepts, the temperature of the universe at the moment of the hypothetical Big Bang was approximately 1.4 times 10 to the power of 32 Kelvin. A fundamental physical constant, this value is referred to as the Planck temperature. Contemporary physics is not capable of defining a substance of a higher temperature, as physical laws are distorted beyond any recognition in such incredibly harsh conditions, quite beyond our imagination. Getting back to WR102, judging by the data we have on stellar evolution today, this star is in its autumn years now. As opposed to main sequence stars, Wolf-Rayet stars do not expand in their final stages of life. Their substantial mass holds all the star's material together in a dense and hot ball. However, after losing a lot of its mass through stellar wind, the object will eventually get destabilized. If current estimates are accurate, WR102 appears to be ready to go supernova at any point in the next 1,500 years. Bearing in mind that the distance between the star and the Earth is 10,000 light-years, it is highly likely that the event has already taken place. A supernova would have been accompanied by an extra-powerful gamma-ray flare. Fortunately, our planet is too far away to suffer any pernicious effects of this dangerous emission. WR102 is comprised of rather heavy chemical elements and even iron. Its later evolution will force it to contract to a critical point. The great explosion bringing the star's life cycle to a close will unleash processes of robust proton and neutron capture. This way, still heavier elements form, including transuranium ones. Eventually, WR102 will be replaced by a neutron star, a celestial body unbelievably hot and dense. The former star's outer layers, disrupted by the explosion, will form a nebula. Slowly cooling off, it will give off heat to the space around it. Many billions of years later, this material will be able to form a new planetary system. It goes without saying that to detect a celestial object that absorbs all light shed on it is a challenging task, to say the least. That is why there are not that many confirmed black hole candidates today. Still, mathematical modeling shows that their number in our galaxy may reach 100 million. This may seem an incredibly big number, but since there are 200 to 400 billion stars in the Milky Way, it makes us realize that in all these expanses, black holes are objects one doesn't come across that much. In one of our previous videos on the topic, we mentioned that a star, the progenitor of a black hole, has to have a mass of at least 18 to 20 solar masses. Only this will ensure a powerful enough supernova to compress the scorching hot core of the star to an exceptionally dense clump of material. After this has occurred, nothing will be able to stand up to the object's gravity force and escape beyond the boundaries of a conventional sphere predefined by the so-called Schwarzschild radius. What used to be a star transforms into a bizarre object with an inner makeup that would defy description by the physical laws we're familiar with. The object, referred to as A0620-00 or V616, is one of the black holes closest to our Earth that we know of. It lies 3,300 light-years away from our planet and forms part of a binary star in the constellation Monoceros. The other object in the system is an orange dwarf with a mass half that of the Sun. Every 7.75 hours, it completes a full orbit around an invisible object of unknown nature. Estimates show the mass of this invisible object to be around 6.6 times that of the Sun. It is admittedly too much for a neutron star. This leads one to believe that the bizarre invisible object is more likely than not a black hole. In addition to getting deformed and elongated by the more massive neighbor's gravity, the orange dwarf is also getting stripped of the outer layers of stellar matter. Spiraling streams of scorching gas gradually flow to the black hole and form a bright accretion disk. It is thanks to this dazzling disk that the black hole was detected. There are at least several dozen stars in the environs of V616, some of which almost certainly have their own planetary systems. It is highly likely that in the future, one of these stars will get dangerously close to the black hole and as a result will be sucked in by the object's insane gravity. This unfortunate star will have no choice, and in this case, the same slow demise is eventually awaiting the black hole's new companion as that of its current one. The process of interaction of a black hole with other objects largely depends on their mass ratio. The smaller the distance between them and the more massive the black hole, the stronger the influence of its tidal forces over its companion. The star may be deformed by them and get stretched towards the system's common mass center. They can also form channels that would carry stellar matter closer to the black hole, adding up to its accretion disk. If the tidal forces happen to be strong enough, they may well destroy the object that is being sucked in by turning it into a fiery ring. It is assumed that there may be planets orbiting a black hole, just as if it were a regular star. In contrast to a widespread opinion, black holes are actually not able to suck in all objects around them indiscriminately. From the point of view of gravitation, in astronomical terms they behave just like any star with the same mass. That is why, incredibly though it may seem, a black hole may well have a stable planetary system. There are several ways for them to form. Firstly, new celestial objects may originate in a nebula of gas and dust that is formed after a supernova. Influenced by gravitation, they first form clumps of material that collide with each other and attract cosmic dust. As a result, they eventually turn into planets and satellites, as well as large numbers of small celestial objects like asteroids and comets. The radiation of the black hole's accretion disk may be powerful enough to warm them and even melt ice on their surfaces. Hypothetically, a planetary system like that could be favorable enough for life to originate and, with any luck, evolve. Secondly, when a black hole captures and destroys another planetary system, some of its objects may choose to take up stable orbital positions around their new host. Of course, this makeover would bring about dramatic changes on the celestial object's surfaces. Thus, an ice giant may transform into an ocean planet, and a gas giant may lose almost all of its hydrogen and turn into a Chthonian planet. Thirdly, space wanderers like rogue planets or interstellar asteroids may also be ensnared by the massive object's gravity. Even though systems like that have not yet been discovered in practice, there is no reason to suppose they are non-existent. If, on the other hand, a planet is too close to the system's center, and the black hole is massive enough, other factors come into play. A scorching hot stream of material forming the accretion disk will strip the celestial object of its atmosphere, and its friction will slow it down and pull it still closer to the black hole. Eventually, extremely powerful tidal forces will rip the planet to tiny shreds. The debris will be pulled into the accretion disk and gradually melt in the hot gas around. In the end, they will inevitably get swallowed up by the black hole and, in essence, become part of it. It is posited that there are three main types of black holes to be found in the universe that are different first and foremost in terms of their mass. The first type can be found in the center of most spiral galaxies. These are gargantuan black holes with masses reaching several billion solar masses. The density of matter in the central part of a galaxy is generally extremely high, which is the reason why there originate a big number of large and bright stars quite closely packed. As they rapidly burn out, they transform into black holes, which in their turn rapidly grow and often merge with each other. As a result, supermassive objects are born, which are surrounded with giant accretion disks made of scorching hot material. They illumine space so brightly that it makes them seen from billions of light years away, even if their galaxy is completely unobservable to us. These objects are known as quasars. The second type is much more widespread, but at the same time, black holes like these are not that easily detectable. Their masses are close to those of stars, and they form out of large stars at the end of the latter's life cycle. By devouring other celestial bodies and interstellar gas, these objects gradually gain in size and eventually turn into intermediate mass black holes. They can also merge together, which generates gravity waves that distort space many light years around. The third type is the hypothetical primary black holes. Their existence has been inferred from today's theory of universe's origins and evolution. Fluctuations in matter that filled space in its early stages of evolution may have been favorable for black holes of infinitely small size to originate. It should be mentioned that according to estimates, the smaller an object of this type, the faster it evaporates, and at the end of its life cycle it turns into a tremendously powerful electromagnetic impulse. Modeling shows that primary black holes with masses around 10 to the power of 12 kilograms are supposed to be flaring up sometime around now, but to date, no such event has been registered yet. According to a certain hypothesis, a microscopic black hole may form on collision of extra-high-energy elementary particles. This variety is referred to as quantum black holes. Still, the conditions necessary for such an event to happen are impossible to be reproduced in lab conditions, and estimated life expectancy of these hypothetical objects is so small that it can hardly be measured with today's latest and most advanced methods. That is why quantum black holes still officially exist only in theory. Of course, it is extremely difficult to detect such dark and compact objects. Some of them happen to have a star companion, whose anomalous trajectory of movement gives telltale prompts of there being an invisible thing in close proximity. Another popular method of detection is observation of accretion disks. These object spectra have some typical features that allow telling them from other sources of light in space. Sometimes we're lucky enough to get a snapshot of a disk with a black spot in it that is evidence that the observed object's structure is quite unusual. A black hole may also be detected thanks to the gravitational microlensing effect. This involves detecting the massive invisible object as it transits between the Earth and a remote star. This changes the star's spectrum in a special way. But admittedly, this method requires a number of rare factors to successfully work. In terms of the vastness of the cosmos, our planet is just a small rocky fragment traveling at incredible speed through boundless emptiness. For billions of years, it has been orbiting the Sun, maintaining a distance of about 150 million kilometers. However, the true size of our system is much larger. According to modern concepts, its outer boundary, which is considered the far edge of the hypothetical Oort cloud, is at a distance of about 100,000 astronomical units. Beyond this boundary begins the vast abyss of the interstellar vacuum, space so rarefied that there is on average only a single hydrogen atom per cubic centimeter. The distances between the nearest stars in our part of the galaxy are a matter of a few light years, and a photon that has left the Sun can reach Proxima Centauri without ever colliding with a particle of matter. This vast void is a pervasive and integral part of the deep structure of the cosmos. It permeates the entire Milky Way, separating stars and planets, black holes and white dwarfs, super-dense pulsars and scattered nebulae. If you move outside the galaxy, you can see that it is surrounded by an even deeper vacuum. For example, between us and the Andromeda galaxy lies 2.5 million light-years of exceptionally rarefied space. This distance is so great that 25 galaxies like ours could fit in it, yet it is filled only with the deepest cosmic vacuum. And this is only a small part of the great cosmic abyss. The Milky Way, the Andromeda Nebula and the Triangulum Galaxy, as well as about 100 of their satellites, are bound together by pervasive invisible threads of gravity. This structure is called the local group and is a large cluster of cosmic matter about 10 million light-years in diameter. The local group, in its turn, is part of an even larger formation, but a relatively small galactic filament by the standards of the universe, called the local sheet. This flattened structure, consisting of several hundred galaxies, has a diameter of about 46 million light-years, and its thickness is roughly 5 million light-years. The sheet is also part of an even larger association called the Virgo supercluster. However, very close to the local sheet, outer space suddenly changes its appearance. Here, the usual colorful universe is harassed by a giant black abyss known as the local void. In fact, the local sheet is one of its walls, the other conventional boundaries being the Perseus-Pisces supercluster and the Pavo-Indus supercluster. At the same time, the void is divided into conventional parts by several rarefied galactic filaments, and wide passages link it into a single network with the neighboring Sculptor and Hercules voids. Due to the cosmological expansion of the universe and the gravitational influence of the surrounding matter, the volume of the local void is slowly increasing. At present, its diameter is about 150 million light-years, and the distance to the center is at least 70 million light-years. Meanwhile, the nearest edge of this cosmic void is located very close to the Earth, at a distance of about 3.2 million light-years. Due to this proximity, the local void occupies a significant part of our planet's night sky, about 40%. The main plane of the Milky Way, containing many bright stars and large nebulae, covers the central part of this region from us. Still, its edges do remain accessible for observation. In 1854, a dwarf spiral galaxy was discovered a little north of the constellation Hercules. It was dubbed NGC 6503. Later, with the advancement of observation techniques, it became known that it is located in the middle of the local void, and its distinguishing feature is the incredible multicolor appearance. The spiral arms of the galaxy are permeated with bright red clots of heated hydrogen, and shining blue nebulae are stellar nurseries. The center is obscured by clouds of cool gas and dust, which have a noble brown color. NGC 6503 has a diameter of about 30,000 light-years, and its distance from Earth reaches 17 million light-years. Due to the gravitational pull of the Virgo supercluster, this galaxy is approaching us at a speed of about 43 kilometers per second. It is believed that its gradual approach to the local sheet will eventually saturate its space with interstellar hydrogen, causing an increase in star formation. It is estimated that in a few billion years' time, the current number of young stars could double, and the small galaxy will shine with renewed vigor. The motion of NGC 6503 is a clear demonstration of how the voids are likely to have come about. It is believed that the foundations of the large-scale structure of the universe were laid in the first minutes of its existence, at the time of chaotic mixing of matter and energy. Cosmic cataclysms of incredible power shook the young universe, forming local compactions and voids. Subsequently, clots of matter became proto-galactic clouds, and areas of space of reduced density became voids. Over time, the pervasive influence of gravity intensified this contrast, pulling stars and cosmic gas into relatively dense clusters, making the space and voids even more rarefied. Observations show that the vast majority of galaxies formed between 10 and 13 billion years ago. In addition, no significant differences have been found to exist between the age of galaxies located in voids and those that form global filaments. This fact also confirms the modern theory of the formation of the large-scale structure of the universe. Meanwhile, allowing for the cosmological expansion of space, we can assume that with time, the local void will become larger and more rarefied, and the Virgo supercluster will gradually disintegrate into several independent groups. At present, it is an association of about 30,000 galaxies concentrated in a region of space with a diameter of about 200 million light-years. At the same time, the total mass of the cluster is about 1.5 quadrillion solar masses, which is tantamount to about 1,000 galaxies such as the Milky Way. The Virgo supercluster is partially contiguous with two other galactic superclusters, the Centaurus and Pavo-Indus superclusters. At the same time, its other side borders on a vast region almost devoid of matter. It is called the Taurus void and is one of the largest known cosmic voids. It is rather difficult to study this part of outer space. The reason is that most of the void lies in the so-called zone of avoidance, a sector closed off from us by the Milky Way plane. The bright stars in our galaxy outshine the fainter and more distant sources, and interstellar matter absorbs and scatters their light. However, thanks to infrared studies, we do have some ideas about the structure of this void. The diameter of this tremendous void is about 200 million light-years, and the distance to the center is about 150 million light-years. When observing the void, one is immediately struck by the remarkably clear boundary between the relatively empty space and a bright cluster of galaxies located much further away. It is called the Perseus-Pisces supercluster and is one of the largest in this part of the universe. A transition this sharp is characteristic of dust clouds, even though infrared studies do not confirm their presence. In all probability, The clear boundary between the void and the supercluster is caused by gravitation, but the exact mechanism of their action still remains to be found out. Meanwhile, it is thought that the torus void, like most other cosmic voids, is not quite as empty as one might imagine. The way light passing through it is distorted suggests that this region may hide in its depths giant gas and dust clouds, the cradles of future galaxies. According to other hypotheses, huge masses of dark matter, the most mysterious substance in the universe, the properties of which are still not fully understood, may be contained inside the void. According to the most daring ideas, there are clots of antimatter or even more exotic matter with negative mass in the centers of cosmic voids. Nevertheless, despite their boldness, these hypotheses lie outside the boundaries of generally accepted scientific concepts, which makes it difficult to verify them experimentally. Currently, only 2 separate galaxies have been discovered tucked away in the space of the giant void. One of them, UGC 2627, has a spiral structure and resembles the Milky Way, while the second, known as UGC 2629, is an elliptical dwarf galaxy. Both objects are located almost in the heart of the void, at a distance of about 185 million light-years from us. The distance between them is small and is within a few 100,000 light-years. Perhaps there are other single galaxies hiding in the space there, but the Milky Way disk does not allow us to see them. Meanwhile, the Virgo supercluster, together with 4 other superclusters, forms a giant galactic filament called Laniakea. It contains more than 100,000 galaxies and stretches for more than 500 million light-years in space. Its gravitational center is the Great Attractor, a mysterious supercluster of galaxies located 250 million light-years from Earth. In its turn, Laniakea is part of a vast galactic stream, and further out, one can see that most of it is surrounded by a black abyss of unprecedented proportions. The light of distant galaxies is drowned in its emptiness, and even the mysterious and elusive neutrinos take billions of years to cross this cosmic abyss. To be honest, it is hard to believe that despite all the development of observational technology, such a gigantic void was noticed only 10 years ago. The year 2013. The University of Wisconsin-Madison. A team of astronomers led by Professor Amy Barger is working to determine the distance between galaxies. In the process, an unexpected and staggering fact is discovered. It turns out that Laniakea and most of its surrounding superclusters are enveloped by a cosmic void of unprecedented proportions. After making calculations, scientists discovered that its diameter exceeds that of any previously known void. The size of the discovered void turned out to be so enormous that several fundamental cosmological principles were questioned. It appears that the universe is much more elaborate than we imagined. The research done by Amy J. Barger, Ryan Keenan and Lennox Coey has led, in all likelihood, to one of the greatest astronomical discoveries of recent years. Their work has shown that our galaxy, along with its surroundings, is located in the middle of the largest supervoid known to science. It was named KBC, after the first letters of the discoverers' names. Observations show that the shape of the giant void is close to spherical, and its diameter may exceed 2 billion light-years. According to calculations, the Milky Way is located a few 100 million light-years from the conditional center of the Great Cosmic Abyss, and about the same distance from its edge. The discovery of a giant bubble of emptiness surrounding Laniakea helped to explain the paradox that had kept scientists busy for many years. The fact is that all galaxies in the universe are gradually floating apart due to cosmological expansion. Measuring the speed of this motion allows us to calculate the so-called Hubble constant, a fundamental physical constant characterizing the rate of expansion of space. However, if we take the galaxies closest to us to calculate the Hubble constant, it turns out that the rest of the universe is expanding too slowly. On the other hand, if we take distant objects as the basis, the Milky Way's surroundings are moving faster than they should. The discovery of the void has accounted for a lot. The fact is that the galaxies inside it, including the Milky Way and its neighbors, are constantly experiencing additional gravitational influence from objects outside the void. This creates an additional force that gradually stretches our cluster in different directions. It is also surprising that the KBC void is so huge that it comprises not only superclusters of galaxies, but also other voids. For example, the local void, as well as the torus void, are part of its structure. It turns out that compared to other voids, even though KBC looks large, it isn't quite so empty. Nevertheless, according to calculations, even this void is just a barely noticeable dark spot against the background of the observable part of the universe, the diameter of the latter reaching 92 billion light-years. If we look at the global map of the universe, we will see a lot of dark spots on it, close to the KBC void in terms of their size. Most of them easily fit within the framework of modern physical theories, while others show surprising and strange properties, difficult to explain from the point of view of science. And one of the most noticeable riddles of this kind in space is the Eridanus supervoid, also known as the CMB cold spot. It is estimated to have a diameter of 500 million to 1 billion light-years, and it lies at a distance of between 6 and 10 billion light-years from the Milky Way. This means that this formation is one of the most extensive elements of the large-scale structure of the universe. The void is located in the southern hemisphere of the Earth's sky and occupies an impressive area on it, several times larger than the full moon. However, it is impossible to see it with the naked eye. The CMB cold spot is visible only with the help of special telescopes that study the cosmos in the microwave spectrum. Thanks to these, astronomers have discovered that within the spot, relic CMB radiation of the universe is about 70 microkelvin colder than the metagalactic average. This deviation is nearly 4 times as intensive as the strongest anomaly previously recorded, and its gigantic size makes it a truly enigmatic object that requires extensive study. It is now believed that relic CMB radiation traveling through hundreds of millions of light-years of deep vacuum is gravitationally influenced by distant galactic superclusters. This causes the pervasive echo of the Big Bang to lose energy, making the CMB cold spot appear cooler in images than its surroundings. Nevertheless, this effect cannot fully explain the excessive cooling of relic radiation. According to calculations, the attraction of external galaxies can account for only a quarter of the observed deviation. It is assumed that the remaining 75% of the effect may be due to the impact of hypothetical dark matter or dark energy concentrated in the depths of the void. However, it is going to take a while before we can truly unravel